Okay, so here we have it, the really complicated case where you have all four places non-zero. Okay, and it's supposed to be a really hard question, or not hard but long question, right? Because you have to have W1 satisfy y and then 0, 0, 0. W2 will be 0 and then 8y minus 20 and then 0, 0, and so on and so on. And solving all those four questions, that's going to be too time consuming, right? However, we want to take a shortcut by thinking of the fact that all these are first order, right? You see that? It's just first order. It's order 1, x to the first part. There's a constant here. So you can think of the following. What if you had some vxy, and that's second order. We know the generic form of the second order, right? It's a times x squared minus y squared. So that's one kind of saddle. And then let me just write in the form that we just computed. Right? Although it's natural to say that after a, this should be b, but let's just call it c. Doesn't matter. Cxy plus dx plus ey plus f. So I know that for any a, c, d, e, f, it's going to satisfy the Laplace equation that we already know. Right? What if this one ends up satisfying the x ones? Right? Then we might be able to save some time by being able to handle these cases. You see where I'm going with this? All right, let's try it. Okay, so first, v of x0, what's that? V of x0, according to here, you're plugging in 0 into y, so that goes away. So you have ax squared. Y goes to 0, so that's gone. You have dx plus dx. Y is 0. You just get f. And that I want it to equal to? Negative 5x. I want it to be equal to negative 5x. Okay, and I want these to be equal as functions, meaning that they have to equal for any value of x. Okay? So for this polynomial to be equal as that polynomial, the only way you can have it is when this is 0 and this is 0 and d is negative 5. Agreed? Okay. So that says a has to be 0, f has to be 0, and d must be negative 5, if I want. Hey, that's nice, because we already have something that satisfies 0 and then negative 5x. We have it right in front of us. Okay, now let's try to do the other one, v of x5. Now, we already have a as 0, so that's not there. F is 0, so that's not there. And then d is negative 5. So let's try to use the exact same thing. So let's see, we're plugging in 5 into y, right? So we have c x times 5 minus 5x, and then plus 5e, and that has to equal to 5x. Okay. And then I see that, oh, this is 5c minus 5 times x plus 5e. That has to equal to 5x. And again, this equality has to be equality of functions. That's important. I'm not saying that these are equal for some values of x, but for all values of x. That means if you have two lines that are always equal, they have to have the same slope and same y-intercept. So 5e should be, there's no y-intercept here, so it should be 0, right? 5e should be 0, and then 5c minus 5 should be 5. Let's see what that means. 5c minus 5 should be 5. So that 5c is equal to 10, divide by 5, you get c equals to 2. Okay. And furthermore, we have
So E is 0.
E has to be 0, right? E has to be 0. Okay, so I think we figured out all the Vx and y. For this to satisfy both conditions, you're going to have, what is it? A has to be 0, C has to be 2, D has to be -5, E has to be 0, F has to be 0. That's it. So I know that this is going to satisfy this and this. Now clearly this is not going to satisfy this one, because if you plug in 0 into x, it says 0, whereas that's y, right? That's not good. However, what happens if I plug in 4 for x? This is 8y minus 20, exactly same as that one. Yeah. Aha! So what I did was, usually if you have the boundary conditions as linear, you can at most afford to kill 2 places. But that's already a very huge time saver. Yeah. But here I fine-tuned the numbers so that it can even satisfy this one. Right? Yeah, it just doesn't satisfy that one. Okay, so where am I going with this? This is V, and it doesn't satisfy everything. So how should I apply this to simplify our question? Yeah?
I mean, can you say again why you don't have to satisfy the first one?
If you plug in 0 into x, you get 0 here, 0 here, you get 0, right?
Yeah.
And that's not same as y.
Okay.
So this V doesn't satisfy the first one, but it satisfies the 3. Okay.
Yeah.
Yeah, so what do we want to do now? You want to set u as what? You want u x comma y as
V plus 1.
huh? V xy plus w xy. Exactly, that's the point, right? Then Laplacian of u equals to 0 would imply, since Laplacian of v is 0, you would have Laplacian of w 0, right? Okay. What other boundary conditions should w satisfy? W of 0y is u0y minus v0y, right? What's that though? What's u0y?
Y.
Y. What's v0y? If you plug in 0, what do you get?
0.
0. So if you do y minus 0, what do you get? You get
Y.
y. W of 4y would be u of 4y minus v of 4y. And we know that these are equal, right? They both gave us 8y minus 20, right? So what do I get?
0.
0. What would be w of x 0? 0. What would be w of x 5? 0 for the same reason. How many zeros do you have for boundary conditions? 3 of them. So we can just solve by just one separation of variables rather than having 4 other ones. Okay? Is that okay? Now, I also purposely made this question so that it references back to our previous solved question, right? So we already solved this case where you have a Laplacian where u0y is y, and then these other ones were 0, right? Yes?
Why was that uxy equal to vxy plus wxy?
Oh, that's because we worked so hard to have these 3 matched. And if you think about it, w would be u minus v. And because they match at 3 places, that was the result. You get 3 zeros. I told you that you need 3 zeros to solve by one separation of variables, right?
Oh, okay.
Yeah, so now if you have 3 places with zeros, you can just solve it. Yeah. And moreover, we actually solved this question. Wxy, we just solved it in the beginning of today's lecture, right? What was it? It was 10 over n pi sine hyperbolic
1 pi over 5.
Yeah, 4 n pi over 5, right, with sine hyperbolic
No,
of
there should be a
n
negative
pi
1.
over 5. Oh, sorry, there should be negative 1 to the nth power here. Sine hyperbolic n pi over 5 x minus 4.
Yes.
Sine of n pi over 5 y. I actually know that this is the solution that satisfies it, right? So that means u is what? Therefore, the answer, now we can just go straight to the answer by quoting our previous solution. I see that uxy is v plus w, right? V is, what is it? 2xy minus 5x plus all this. Let me just still write it. Infinity 10 negative 1 to the power n pi sine hyperbolic and 4 n pi over 5 times sine hyperbolic n pi over 5 x minus 4 sine n pi over 5 y. Okay, so that's the final answer. Yeah, so we got the answer rather quickly, right, without having to split the Laplace PDE into 4 different problems. Oh, and then let me just stress this again. Are we solving PDEs? No, what are we doing?
Guessing.
We're guessing. We're basically trying to construct a solution that satisfies all the conditions that's given to us. Why are we allowed to do that again? Because of uniqueness. Okay? We have the knowledge that such questions, if you have a Laplace equation with 4 boundary conditions, then the solution would be unique. Okay? Now, I will be proving this in this lecture. Okay, I will prove the uniqueness of such problems and also uniqueness for the wave equation. We already did the uniqueness for the heat equation, right? So if I show you the 2 other ones, then you can confidently say that since this satisfies all the conditions given to us, and we know that the solution is unique, this has to be the solution. That's how we conclude. The only reason such weird way of thinking works is because of uniqueness.